Hello. In this lesson, we're going to be looking at the properties of different exponents. And so I have several different examples here that we're going to try to work through to start our lesson. In number one, we have a to the third multiplied by a squared. Now, if you remember how exponents work, exponents tell you how often we multiply a number together. So a to the third is the same as a times a times a, and we are multiplying that by a squared, which is a times a. Now when we do that, notice we have 5 a's all multiplying together, so I can rewrite that as a to the fifth. Again, exponents are how many times we multiply a number together. We're multiplying a by itself 5 times. All right, let's move on to number 2. In number 2, we have b to the fifth divided by b squared. In this particular problem, we're looking at b times b times b times b times b, all divided by b times b. So what this looks like when we cancel, notice I have a b on top and bottom, I can cancel here and here. And so in the numerator, I have b to the third. In the denominator, when we take a number and divide it by itself, we're left with 1. So b to the third over 1, or just b to the third. So we notice that the pattern here, when we take a to the third times a squared, we can do the 3 plus 2, and that results in 5, which is the same as our exponent. Not a coincidence. When we look at our exponent here, we have 5, and we're taking away 2, and so we can do 5 minus 2 to get 3, and there's our exponent. Again, not a coincidence. In number 3, let's look at it a different way. In number 3, we have c to the 0. Well, how do I consider this? If I look at c to the 0, I can think of c to the, let's say, second, divided by c to the second. If I follow the same pattern I just did, and I did 2, my exponent 2, minus 2, that's how I get 0. And so this should be the same as c to the 0. But what does c squared divided by c squared even mean? Well, you're taking a number and you're dividing by itself, so it results in 1. So c to the 0 is the same thing as 1. An exponent of 0 means you're taking a number and you're dividing it by itself. In number 4, we have e to the negative 5. And I want to look at this as e to the negative 5 divided by e to the 0. Well, I can do the same thing I did in number 2, where I do negative 5 minus 0, and I just get that result of negative 5, so I can leave that as e to the negative fifth, but negative exponents are very difficult to understand. So what if we did it the other way? What if we did 0 minus negative 5, the negative there, and we get 5 instead? Well, if we come up with an exponent of 5, where would that go? Well, we did the 0 first, the 0 being on bottom, so we would need that e to the positive fifth on bottom. Well, what's left on top? What did we just do? We divided a number by itself, and so we get 1. So we get the result of 1 over e to the fifth. All right, number 5, we have f times d to the second power. And what that means is I'm going to take f times d multiplied by f times d. I take a number times itself, right? F times f is f squared. D times d is d squared. And there we're good on that one. G to the fifth, then to the third. We have g to the fifth multiplied by g to the fifth multiplied by g to the fifth, right? We take that g to the fifth times itself 3 times. And we use our process from number 1, where we do 5 plus 5 plus 5, and we come up with 15, and so we get g to the 15th. And then in number 7, we have h over j to the third, which shows us h over j times h over j times h over j. And the result here is h times h times h is h cubed. The j times j times j is j cubed. All right, so let's make these more formal. On this slide, I took everything that we just talked about and transferred it into a more mathematical, formal property or way to look at this. So we see that a to the m times a to the n would equal a to the whatever m plus n is, and so on. Okay? We see that in the fourth one, and I'll highlight that. Here we are. The fourth one right there. I have a to the negative n equals 1 over a to the n. The same thing also applies if I were to have 1 over a to the negative n in the denominator, the negative exponent is there. That's the same as just a to the n. Okay, and the other one we didn't really talk about was down here, this very last one. A to the second power, if I put a to the second in absolute values, that's the same as doing the absolute value of a and then raising it to the second. So what it's saying is, if you were to do, let's say, negative 8 squared, and then do the absolute value of that after, it's the same as doing the absolute value of negative 8 and then squaring. Well, negative 8 squared is 64, and then the absolute value of that is still 64. While on the other side, the absolute value of negative 8 is 8, and then 8 squared is also 64. And the reason this works is because anytime you square a number, the negative times a negative makes it a positive number. I encourage you to pause this screen as necessary and add these properties to your notes before we move on to the next slide. Okay, here I have more examples for you. In number 8, we're looking at 5 to the second, then raised to the 1/2 power. So I can look at 5 to the second raised to the 1/2, and I know that a power to a power, if I take 2 times 1/2, that should give me the true exponent, which is 1. So I just get 5. But let's look at this a different way. If I did 5 squared first, so my order of operations, I just start from the inside, the parentheses. So I get 5 squared, which is 25. But I'm still raising that to the 1/2 power. I haven't used that yet. So what does it mean to raise something to the 1/2 power? Well, we know we need it to be equal to 5. What's the operation on 25? That gets me 5. And it turns out that 25 to the 1/2 then must be the same as the square root of 25, which results in 5. So if something is raised to the 1/2 power, it's the square root. If I were to take a number and let's say it is, I'll use 8. If I raise 8 to the 1/3 power, that's the same as the cube root of 8. Or rather, what number times itself 3 times gets me 8. If I were to say, how about, let's think about maybe 81 to the 1/4, and that's the 4th root of 81. There we are, 4th root of 81. Or rather, what number times itself 4 times 81, and we get 3 there. So let's use that information and try to solve number 9. When number 9, I'm looking at 16 to the 3/2. Well, I can rewrite this as 16 to the 1/2, then to the 3rd. Right, we have a power to a power, and we know that a to the m to the n is the same as a to the mn. So I basically just went the other way. I know that 3/2 is the same as 1/2 of 3. So I broke this up. If I were to take the 3 times the 1/2 up here, it's the same as the 3/2. Alright, so let's go ahead and attack this problem. If I did 16 to the 1/2, that's the same as the square root of 16, still raised to the 3rd power. And I could do the square root of 16, I definitely know that. That's 4, still raised to the 3rd. And 4 to the 3rd is 64. I know my notes are a bit of a mess here. I hope you understand with the different colors going on there. So let's look at the next slide, which more, again, puts this in a more math type definition here. If we have a to the m over n it's the same as the nth root of a to the m. Now, again, get this in your notes, but if I go back to the previous problem where I had 16 to the 3 halves, and I broke it into 16 to the 1 half to the third, and then did the 16 to the 1 half first before getting 64, I could have done that the other way, though. I could have done 16 cubed and then taken it to the 1 half power. I don't know what 16 cubed is off the top of my head. It's some number raised to the 1 half, and then whatever its square root is ends up being 64. So this is whatever 64 squared ends up being. Okay, again, get all this in your notes, and we are done.